Show by the principle of mathematical induction that for all n belonging to the set of natural numbers, the following expression is a positive integer. Okay, now before beginning, here we need to clarify one thing. We do not have to prove that this expression is a positive integer. Our goal will be to show by using the principle of mathematical induction that this is true statement regardless of whatever natural number we consider. So let us begin. So first what we'll do, we're going to consider a statement and we're going to name it as P of n. So that means what we'll do, we're going to consider the statement P of n. So let P of n be the statement. It's going to be a mathematical statement and this statement is going to be given by, so we have P of n such that we'll consider this expression, which is n raised to the power of 11 divided by 11 added to n raised to the power of 5 divided by 5 added to n cubed over 3 added to 62n divided by 165. So this expression is a positive integer. So what we have done, we have converted our given statement into a mathematical statement which is denoted by P of n. We're going to call this statement number 1. Now let's verify that this is a true statement. So for n equals to 1, that means we will check whether if the statement is true for the first natural number, we have P of 1 such that we're going to replace n with 1. That gives us 1 over 11 added to 1 over 5 added to 1 over 3 plus 62 over 165. So let's add it up. That's going to give us 1, and we know 1 is indeed a positive integer. Fine. Now that the statement, this simply tells us the statement P of n, this is going to be a true statement, but it's going to be true for only one natural number, that is n equals to 1. We will need to verify that it's true for other natural numbers as well. So here let us suppose that n equals to m. So we're considering another natural number m such that the statement P of m is true. We're considering P of m to be a true statement. Now P of m being true, so this simply means that we have P of m such that m raised to the power of 11 divided by 11 added to m raised to the power of 5 divided by 5 added to m raised to the power of 3 divided by 3 added to 62 times m divided by 165. Now this expression is a positive integer as well. This is also a positive integer. We're going to label this as statement number 2. Now using this statement, we'll have to verify that if we consider the next consecutive natural number m plus 1, then P of m plus 1 is also true. This is our goal. We'll have to show that P of m plus 1 is a true statement. So in essence, what is P of m plus 1? P of m plus 1 such that we have m plus 1 whole raised to the power of 11 divided by 11 added to, we have m plus 1 raised to the power of 5 divided by 5 added to m plus 1 whole cube divided by 3 plus 62 multiplied to m plus 1 divided by 165. This expression is a positive integer. So this is what we need to show. Fine. Now how do we show that this is a true statement? In order to show this is a true statement, we have to take the help of statement number 2. Now using statement number 2, since we have already mentioned that this expression is a positive integer, so what we'll do, we'll suppose that m raised to the power of 11 over 11 added to m raised to the power of 5 over 5 plus m cube over 3 added to 62m over 165. Let this be equals to some constant lambda, where lambda is a positive integer. Right? We're assuming this is a positive integer. Now using this, we will try to verify number 2. Now in statement number 3, we have m plus 1 raised to the power of 11 divided by 11 added to m plus 1 whole raised to the power of 5 divided by 5 added to m plus 1 cube divided by 3 plus 62 times m plus 1 divided by 165. So we'll take the help of this equation. We're going to call it number 4. We'll take the help of number 4 and we will show that this expression is also a positive integer. Now, expanding the first term is going to be an Herculean task, but what we'll do, we'll consider the factor 1 of 11. We'll not take the expansion of each and every, we'll not consider each and every terms of the expansion. Rather, we will consider only the first term, which is going to be m raised to the power of 11, and then we have the remaining terms and the last term, which is going to be 1 raised to the power of 11. Similarly, for the second term, when we expand it, we have 1 over 5 multiplied to, we'll consider the first term, which is m raised to the power of 5. We have the rest of the terms, and then we have the last term, which is 1 raised to the power of 5 added to. We have 1 over 3 multiplied to m cube plus 3 times m squared plus 3 times m added to 1 plus 62 over m times 165 added to 62 over 165. Okay, now what we'll do, we'll take the first term of each of the expansion. So we have m raised to the power of 11 over 11 added to m raised to the power of 5 divided by 5 plus m cubed over 3 added to 62m over 165. So let this be one single term. We'll combine them, and then we consider the last term, which is 1 over 11, last term of each of the expansion. So here we have 1 over 11 added to 1 over 5 added to 1 over 3 plus 62 over 165, and then we have the rest of the terms. Now luckily for us, now if we consider the first expansion, that means expansion of m plus 1 raised to the power of 11, excluding the first term and the last term, whatever terms we have in between, the coefficients are going to be divisible by 11. Each of them are divisible by 11. So that means that's going to leave us with only some integer values. That is going to be true for the second expansion as well, for the third expansion as well. As you can see, in the third expansion, we have 3m squared plus 3m. So if we divide it by 3, so that leaves us with m squared plus m, which is an integer. So we'll simply state that it's an integer value. We don't have to worry about this exact value. Now, this expression, we have already considered this to be equals to lambda according to number 4. We can replace it with lambda. Then the sum of these 4 terms, that's 1. So we have lambda plus 1 plus some integer value. Now, since lambda is an integer, 1 already is an integer, their sum is going to give us some positive integer value. We don't have to worry here what's the exact value. All we have to worry about is if it is a positive integer or not. And yes, we have obtained a positive integer, which means that our statement p of m plus 1, so this is going to be a true statement. And if it is a true statement, then we can generalize it and we can say that the statement p of n, this is going to be true statement, and it is going to be true for all values of n belonging to the set of natural number, meaning any natural number that we pick up, the statement p of n, this is always going to be a true statement, hence proved.